bind up free hormones. They are going to provide negative stimulation to immune cells in the environment. They are going to release hormones that help turn things down, that stop B cells and T cells from doing what they're doing. Typically, they're going to secrete interleukin 10 and TGF beta as suppressive hormones. That gets our immune system to chill out. Some of these subsets of cells work together and can influence each other. There are situations where there is cross-regulation of different subsets of helper cells back on to each other. But it turns out the amount of hormone and the cocktail in the environment, the mixture of hormones in the environment, help the cells decide, help them know for sure which pathway they want to travel down, right? So are you exposed to more TGF beta? Are you exposed to more IL-6? Whatever the balance is going to help tip the cells in the direction for the population that we need. Our follicular helper cells. These guys are going to foster the growth and development of B cells in follicles in secondary lymphoid compartments. There are a subset of hormones that help support those follicular stimulators that they also in turn secrete to support the growth of B cells there. While this is cool, what I think is most important is that you really understand for sure what the jobs are of T helper type 1s, T helper type 2s, and T regulatory cells. Those are the most important traditional T cells for you to think about in everyday immune responses and challenges. Molecular helper cells are cool, Th17 helper cells are cool, but not as common in everyday responses. As you're exposed to these hormones, as we're building our clone army, whose effectors, whose memories? Are you helper 1? Are you helper 2? What are you becoming? This may not be a permanent decision for the cells. This could be fluid. I'm in this environment, I'm receiving more information that tells me to be T helper type 1. Okay, great, that's what I'm going to do. But I go to this other place and I'm working here and I'm getting new hormones that tell me no. Stop doing that. Be something else. It's absolutely possible that the cells can change their mind in the context of the reaction that they are fighting at a given time. So just because you set down one pathway and you're doing a particular job doesn't mean it's permanent. Doesn't mean you have to stay that way forever. Even to a certain extent, it is probably possible for CD4 and CD8s to decide to become something else if they have to in the periphery. That is all still possible. This is a really cool example of showing us how important it is to make the right subset of helpers during the right immunologic challenge. The example here is leprosy. The bacteria that causes leprosy is called Mycobacterium leprae. And Mycobacterium are fascinating bacteria. They're named Mycobacteria. They have some fungi-like properties. They often cause intracellular infections. Walking pneumonia is caused by a different type of mycoplasma, which is much harder to treat and much harder for people to get over, right, than typical streptococcal pneumonia, which you get very quickly, rapid onset, you're very sick, and you take an antibiotic and it goes away, and you're all better. Walking pneumonia is exactly walking pneumonia, because you got it for weeks, and you're hacking, and you're coughing, and you're like, what's wrong with me? And you just keep getting worse for weeks and months. Mycobacteria grow slowly. They cause intracellular infections, which means they avoid immune detection for longer and can persist for longer periods of time. Leprosy does the same thing. It gets inside epithelial cells of our tissue and starts replicating there, causing damage to those tissues. There are two forms of leprosy that happen to people when they are infected. The first form is called tuberculoid. In tuberculoid infection, our immune system, both innate and adaptive, wall off the bacteria in tubercles. Your tissues start building these little scar tissue cells to package the infection, to wall it off, to keep it in an area so that it can't keep spreading to neighboring tissues. If people get tuberculoid leprosy, they often look normal, their disease doesn't progress, and often their immune system can cure them or keep the disease from spreading. Because you build these little walls, scar tissue walls, to keep the infection in one particular place, in one group of cells, instead of allowing it to progress. There's also the lepromatous form of leprosy. This is the type of leprosy that we think about when we think about the Bible or the movie Cool Hand Luke. Your tissue is destroyed. It's gone, right? People are missing all sorts of ears, fingers, nose. Tissue is gone. Why? The tissue gets destroyed from the infection. Bacteria grow, they replicate, it causes necrosis in the tissue, necrotic damage spreads and spreads and spreads. The tissue gets necrotic and it falls off. The immune system is not capable of walling off the infection and protecting you from spread. It continues to spread. What decides? What decides if you have tuberculoid or lepromatous form of leprosy infection? It's not the bacterium, believe it or not. It's you. It's your genes, how your immune system decides to respond to that infection. If your APCs present bacterial antigens through MHC2 and they activate IL-12 and the right hormones to support T helper type 1s, you create active NK and cytotoxic cells that wall off the infection and slowly kill it from the outside in, protecting your tissue, protecting you. If your APCs present antigen and provide IL-4, they're going to switch your immune response to be more B-cell oriented instead of cell-mediated. B cells are going to make antibody. Antibody is going to float around your body. Where are the bacteria? They're inside your cells. Can antibody get inside cells? Cannot. So you just shifted to an immune response to make antibody to try to kill an intracellular pathogen that you're never going to be able to kill that way. Because antibody can't get in there. Unfortunately, your immune system made a mistake. It chose wrong. It chose the wrong path, which unfortunately allows the infection to continue to spread, causes damage and necrosis and loss of function to your tissues. So it's the decision that your immune system makes that dictates whether or not you get better or not. Now that we know this, we know that we can supply supportive cytokines to people to help pump up cytotoxic reactions or B-cell mediated reactions. But we have to sometimes help our immune systems because they may not get the right key. One reason is some infectious agents have genes for making hormones that suppress our immune responses. Epstein-Barr virus, mono. Virus gets inside you, once it's replicating inside your cells, it forces your normal body cells to produce IL-10. Guess what IL-10 does? Turns off B cells, turns off T cells, makes everybody go to sleep. Virus gets in, turns off your immune responses, and then you end up really, really sick for a long time because your immune system doesn't know to respond because the virus is turning it off. Okay, same thing happens for lots of viral infections. Viruses get inside, train our immune systems to make weird hormones or make weird hormones that turn off our immune responses or make our immune responses go in the wrong direction, which prevents us from getting well, which prevents us from killing off the cells that harbor the infection. This is particularly insidious. HIV does the same thing, forces your cells to make B cell responses instead of T cell responses. Virus is hiding inside T cells, no T cells get killed, virus continues to propagate over time and expand and spread and make you sicker and sicker. Okay, so how do we know? How do we know the difference between a naive cell, a naive effector, a naive memory cell, a T helper type 1, T helper type 2, central memory cell. How do we know who all these cells are? We look at your cell surface receptors. We ask, what markers are you displaying on your surface? That tells me who you are, where you hang out, what your job is. Right? But I have to capture the cells and I have to stain them to see what they express at any given time. Okay, so while T cells are being made, we are going to make some subsets of cells that are referred to as central memory cells and effector memory cells. Central memory cells are always going to reside in secondary tissues, and they are always going to be waiting for secondary antigen exposure. So these are the guys that get made initially early on in infections, but they always stay in secondary tissues. They are the reserves. They know we will wait to be called. Years from now, we will wait to be called. Effector memory cells, on the other hand, fall into a slightly different category. They can travel to tertiary tissues, and what they're waiting for is effectors are fighting the battle. What if some of the effectors are damaged, if they're dying, if we need more cells? They are waiting there as a backup to the first one. So we've got essentially like two levels of reserves. We've got the you wait for a long, long time. You're going to carry and hold the information and be the master regulator. And then we have another set of troops who have been trained. They can act as memory cells, but they're going to serve as a backup. Let's say the infection inside our bodies is taking a very long time to progress. We have long COVID. And we have to have wave after wave after wave of activated T cells to hunt and kill, to find all of the infected cells in our body. It could be in our respiratory tract, in our cardiac tissue, in our vascular tissue, in our liver, in our lung. We got to go all these places. Who is keeping the waves of troops? Who keeps pumping them out? These guys. Right? So if it's not over in a week, if it's over in a month or 2 months, these guys have been the backup source of information for long periods. How memory cells arrive is still mysterious to us. There's still lots of information for us to learn about what specific subsets of genes, what hormones are helping to regulate these responses. There are a lot of proposed ideas. Some are the cells that are memory cells are made right away, very early on. Some folks say no, they're made later on when the right hormones, the right things are happening, who knows. Some say that the central memory cells actually come from effector memory cells. Some people say no. It's very hard for us to be able to perform experiments with the current information that we have now to definitively know the answers to these questions. But memory cells are a self-renewing population. So they act like a stem cell. They do have a limited life, but they can continue to provide clones essentially for as long as you're living over time, right? So really cool experiments were done looking at survivors of the 1918 flu pandemic. Looked at septuagenarians, octogenarians, nonagenarians, and asked, do you guys still have memory of the 1918 flu strain? Yep. They still have memory B cells, memory T cells that can make effector cells upon stimulation. So a lot of those people that were testing, right, they hadn't been exposed to flu virus for 80 years, but they could still activate those memory cells. So your memory can be long, long lived for a long, long time. Okay, this is essentially the chapter. Okay, so now we've been through all of the material that we will be tested on next week. Go through your review sheets, chapter 7, 8, 9, and 11. Try to figure out where are the holes in your knowledge. Come to class on Thursday. Ask lots of questions. Email. come to office hours, ask lots of questions. I will help you sort it all out, but this is the material that we'll be tested on. All right, have a great day.
Saturday I still have a morning class, but Saturday afternoon. Are you here for that Saturday morning class? Do you want to go? Yeah. I mean, yeah.
What time you want it? What time do you want it? Okay. Awesome, actually. On Saturday during the day. So, I just plan to be here earlier. I drop off.
So I'll just go ahead and text you whenever I'm done.
Okay.
Yeah, and whenever you're
Package up stuff here, and I'm gonna go right to my office.